My goodness, it's about time we got into the it ain't voodoo part of this mass spectral odyssey. So let's get started. You will recall that this is another tool in our spectral characterization of molecules. We have crazy wild molecules that we can use IR and NMR on, but one thing that IR and NMR can't do is give us the mass of the molecule. That's where mass spec comes in, blowing the molecule to bits, but the point of this mini lecture and Interchapter G is to convince you that the blowing apart of the molecule actually isn't random. A little bit of a recap, and super important to emphasize, is that it all starts with the molecular ion, where that globo electron density is hit with energy. You kick out an electron to get something that's the same as the original sample minus one electron. So that means I have an odd electron, so I have a radical, and it means since I lost a unit of negative charge, I have a cation. That's our molecular ion, M plus dot. So that first bit of information, if you can spot the molecular ion, you know the molecular weight of your sample. The second super important thing to remember or point out is that we're going to dive off into some electron movement like you have never seen before. And this is not the same. And it is the same. It's the same kind of electron movement. It's just that the stability of the fragments that are formed are really, really wildly high energy. It's not beaker chemistry. So we will see primary carbocations. We will see primary radicals. It's not unusual to see those in mass spec because this is super high energy. And finally, we want to keep in mind this fundamental truth about mass spec. Your molecule falls apart into two different kinds of fragments. There are charged fragments that are invariably positively charged. Those are the ones that are actually seen in the mass spectrum. And then there are the radical pieces that are broken off. They go away. They are not charged. They just have an odd electron. And therefore, since they aren't charged, they are not detected, and you do not see them in the mass spec. All right, so high priority. We want to have an idea of what our molecular ion looks like. In other words, once I hit that glob of electron density with 70 electron volts, where do I lose that electron? Where am I left with an odd electron? And that's actually fairly reasonable in that we know that orbitals containing electrons are at different energy levels. That sigma electrons deep in the core of the molecule are very stable. It's hard to get rid of one of those. Pi electrons in a pi molecular orbital, kind of on the outside of the molecule, pretty easy, well, easier to kick one of those out. And the lone pairs in the non-bonding orbitals, those are quite vulnerable to being kicked out by 70 electron volts. So, if I think about cyclohexane and what the structure of the molecular ion might look like, I would envision that once I hit this with 70 electron volts, I will most likely lose an electron from one of the lone pairs, leaving, as you can see, an odd electron right there on the oxygen. Now, I have no idea if this is true. I cannot possibly look into the mass spec and see that little electron missing. But based on what I see in the spectrum and the analysis of the spectrum, it makes sense that that's where the odd electron is located. How about 2-butene? Well, based on what I've said so far, it does stand to reason that we're going to lose an electron out of the pi molecular orbital. And keeping in mind that an alkyne, or any bond really, is just 2 electrons, then if I hit this with 70 electron volts, I take one of those away, and that gives me a molecular ion structure that I could propose looking like this. Now, it's totally legitimate to ask, why does it look like that? And maybe not like this. Why don't I put the plus over here and the dot over here? Hey, that's also completely reasonable. As I said before, I cannot possibly imagine exactly how this thing blows apart. But I do believe that the pi molecular orbital is the highest energy orbital in this molecule, and that's where it's most likely to localize that one odd electron. So that is fairly random, but with the knowledge of these particular molecules and what we know about energy levels, we would predict the molecular ion structures to look like those shown. Why is that important? Because once we know what the molecular ion looks like, we can look at a mass spectrum and say, ah, I have confirmatory data here that suggests I really do have sample X. So let's start looking at examples. Here is the mass spectrum for hexanes. So hexane, I should say, just plain old normal hexane. And as you can see from the mass spectrum, the base peak here is right at 57. Well, that's very interesting. What fragment ion is responsible for that signal? That's what I want to know. I want to be able to say that I can confirm the structure of hexane. Well, the molecular weight of hexane is C6H14, which is 86. So what this is telling me is that I lost a fragment that weighs, if you will, 29 mass units. So let's go back to this. Here is my molecular ion at 86, and something minus 29 was lost from the molecule to give me this base peak at 57. What could that be? Well, here is a proposed structure for the molecular ion for hexane. Now, keeping in mind that hexane is nothing but sigma bonds, I have no choice. I have to kick an electron out of a sigma orbital. I am choosing to localize it between carbons 2 and carbons 3 because once I have blasted that poor little sigma bond into oblivion, then this thing can fall apart into the ethyl radical and this butyl cation. So this is C4, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 4, 48 plus 9, 57. And this is 29. This is not detected. I lost it. What is detected is my butyl cation. There you go. That explains the base peak in the mass spectrum for hexane. So, point number one. What is lost is often just as informative as what is left behind and detected. So if I can find my molecular ion and I see that there's another peak at M-1, then that implies I kicked out a hydrogen atom. If I can find my molecular ion and I see that there's a big peak at M-18, that's strong evidence that I have somehow or other lost a molecule of water, and so on and so forth. So these masses are typically, or quite common masses to see lost in a mass spectrum. In addition, then, there are some pretty common signals that are found or seen in a mass spectrum. So these are the ones that are, in fact, detected. So, a mass to charge signal at 15, boy, that's absolutely bells and whistles for a CH3. If we have not the ethyl radical but the ethyl cation, well, that'll show up, and that'll show up at 29. So as you look at these charts, you will start to recognize certain structural fragments that give you a clue as to what might have been in your original molecule. All right, so given that, predict the base peak for this molecule. And the way we start is by thinking about, lone pairs, pi electrons, sigma electrons. Well, obviously, we only have sigma electrons, so we're going to have to kick out an odd electron from one of these sigma bonds in such a way that makes the most sense in terms of stability. Well, what I look at here and see, boy, it makes real sense to me that it's pretty likely that I would see a tertiary carbocation and this radical. Maybe. If I expect to see this fragmentation from formation of the molecular ion as shown here, so basically I'm zooming in, focusing in right here on that bond, kicking an electron out of that bond to make this molecular ion. If that is correct, then I should see a base peak at C4H, 1, 2, 3, 4, 5, 6, 7, 8, 9, H9, which is 48, oh yeah, 57. Another common number. Is that true? Well, there's the tert-butyl carbocation, and there's the mass spectrum. So yay, absolutely what we would expect. So that's good confirmatory data that we actually saw that we have the right molecule. And as was pointed out in the previous mini lecture, this is a tricky one in that there's no molecular ion showing up because it fragments so quickly. Alright, alkenes and aromatics, of course, alkynes as well, they all have pi electrons. So that's where we're going to go first. We're going to lose electrons from the pi molecular orbital. So we would predict that if we're going to kick an electron out here, it's going to come out of the pi bond. In so doing, we get this, or, oops, no, not that, this. And since this is a symmetrical molecule, it doesn't matter. And in any case, what we would hope to see is fragmentation to give us some fragments detected in the mass spectrum. So what would we expect to see? Well, you're going to start and now you're going to use your radical electron movement, and you're going to kick off one piece. So it makes sense that I would see the formation of this very stable allyl cation, and I will lose the 15 mass unit methyl radical. So what will be detected? This guy right here. This will not be detected. I will see an M-15 peak. So that's what we'd expect to see for E3 hexene. How about 1-pentyne? Well, there's the the molecular weight, I should say, for 1-pentyne, 68. And where would I expect to see the molecular ion form? Well, certainly from the pi molecular orbital. So let's say we lose an electron to give us this guy and this guy. And, then what do we have? Well, we have CH2, CH2, CH3, and using, again, our radical electron movement arrows, pop that guy down. He gets matched up with this guy over here. So, based on that fragmentation mechanism, I would expect to see in my mass spectrum this cation and loss of that radical, the ethyl radical. So I would expect to see an M-29 peak in my mass spectrum, which corresponds to that guy. Now, there she blows. There's the M-29 structure. What you want to think about is, how could I get an M-1 peak for this particular molecule, 1-pentyne? Propose a mechanism. All right, example 3, ethylbenzene. Now, you got lots of pi electrons in an aromatic ring. What am I going to do? Where am I going to kick one out? It's totally arbitrary. I can't predict. I cannot see where these might be. If I start with this one, I think it makes sense, as usual, to pair these up as shown. So you're always doing this. You're always taking an atom X that's bonded to atom Y and atom Z. You're plopping that guy down in, and one bond over, you're homolytically cleaving to kick out Z radical, and you're making an XY over here. So that's what we're doing, and in so doing for ethylbenzene, that would result in something that looks like this. Minus the methyl radical, so M-15. And what we end up seeing is a huge M-15 peak in our mass spectrum at mass to charge 91. And it turns out that that's really common for this kind of molecule. And it's called the tropylium ion because it's aromatic. And I can delocalize that positive charge all through the 7-membered ring. So that's a fairly abundant peak in the mass spec. So those are some fragmentation mechanisms to get you started in mass spec. Just rely on your fishhook electron movement arrows and break some bonds.